Hello and welcome to AWCI's webinar. My name is Tan, AWCI's Education Program Manager, and today's presentation is Seismic Requirements in Suspended Ceiling Design. Today it's my honor to introduce Michael O'Donnell. Michael is the Seismic Manager for USG. He joined the company in 2005 as a contractor specialty representative for USG ceilings. He trained and educated architects, contractors, and distributors on all USG ceilings. Prior to USG, Michael was a general contractor for 10 years. He has also been in and around construction industry for over 35 years with a focus on seismic ceiling for the past 12. Next time you'll see Steve Bell. Steve is the product manager for suspension system for USG. He joined the company in 2017 as a technical specialist working on high-end custom ceilings. Prior to USG, Steve spent a decade-long career in architecture, working in multiple market sectors, including K-12 education, commercial office, automotive, and residential. So, without any delay, Steve, off to you.
Thanks, Tal. Appreciate it. Thank you for having us. Thank you, everybody, for being a part of the presentation. My pleasure to kick things off with to introduce seismic requirements of suspended ceiling design. Like Tal mentioned, my name is Steve Bell. I will be a panelist and co-presenter today. I am the product manager for suspension systems with USG. I've been with the company for 6 years, like Tal mentioned, and prior to that, I've had over 10 years of experience in architecture. So I'm well aware of the challenges associated with seismic design and specifically seismic design for ceilings. I'm excited to introduce you to your presenter today, Michael O'Donnell. Michael is our seismic manager at USG, who's responsible for managing our seismic strategy within the company. He's a fantastic resource when it comes to the topic. He lives it day in and day out, and it's my pleasure that he's here with you to lead us through this presentation. So with that, I turn things over to Michael. Go ahead, Mike.
Thank you, Stephen. I appreciate it. And thank you, AWCI, for inviting USG to present seismic ceilings and seismic ceiling solutions and everything that goes on with seismic. I thank you for attending in this as well, the audience. So without further ado, what we'd like to do is take you through the path of seismic design and how we get there, and then also how it looks at the end. So we're going to start this off. We're going to go through the agenda of define the goals of seismic design. We're going to describe the variables within the design criteria. And then we're going to discern the differences in geographic locations. And even though geographical areas is in the variables, there's also significant amount of design work that goes into the geographical locations of where we're going to build. And then we're going to disseminate the ceiling installation requirements for our application for where we are in the industry as far as the ceilings installers. Right now, we're going to define the goal of seismic design using data and technology to build better. So we like to use data and technology. It helps us do things better. It helps us create and design better. And when we're talking about seismic, we really need, and we can tell by what's going on in today's globe, that we really need good seismic design criteria so that we can do what? Build safer communities. We want to have safer environments that we live in and we socialize in. And so we're going to track some data over time, and we're going to look back and see where we've come from and where we're at today, and see how we've used the data to create safer communities. Okay, so back to here's where we're at. We're going to define the goal, the seismic design, and using it to design better, to build better. This is where we want to look to see where we build safer communities. And so here's where we're going to start tracking our data. So we look back, and something that sticks out in our mind is the 1906 San Francisco earthquake. And in today's environment, we can see all the way up to Turkey. Well, it just happened in Turkey. And so we're seeing more and more earthquakes happening across the globe. And we're seeing it with more frequency. And so what we're trying to do is develop systems that will allow us to defend or build against these types of outcomes and effects. So in today's environment, we can track earthquakes and seismic events that are happening in real time within minutes. And so on this slide, you can see where we gained some information from a couple different websites, the USGS, the Geological Survey, and we can see here where they post different events that happened around the globe. So down here in the bottom left hand, we can see in Hawaii, February 14th, we had a magnitude 4.8. And then we can look over a few more and see February 13th, we had one in Romania at 5.0. And we look down the center section and we can see down at the bottom, we see the event that happened in Turkey on the 17th. And so we want to keep apprised of what is going on with seismic because it's ever changing and it's ever moving across the globe, and it happens when we least expect it. And some of the things we're trying to do is figure out how to not just design against it, but sometimes try to figure out when they might be happening. So that is on the agenda for the seismic community. And so we've looked over and tracked data all the way back from the 1500s and maybe even before that, from memoirs and different historical documents. And we can see that some very significant events have happened in 1557, one in China. And the devastation is destruction to the buildings and things like that, but the worst outcome is to the people, right? And so this is why we look back in time and go, okay, in 1976, we had an earthquake in China and 250,000 people were killed. And so all the way up to more recent, the event in Japan, where the earthquake happened on the coast of Japan, which caused a tsunami that caused devastation to the nuclear plant and to that area in Japan, and that's how many people. And so the scientists have recognized that we have these earthquakes all over the globe. And so they started putting data together in the 20s and recognizing we need to have some sort of defense or building to where we can stand up and survive some of the seismic events. And so in 1927, the UBC, which is the Uniform Building Code, put in some of their first provisions for seismic and seismic design. And then in 1935, UBC included a map. This is the geological areas or the geographical areas that we see more and less seismic events in. And so that helps us understand how to build and where to build. And then in 2000, the UBC was replaced by the International Building Code. And that invoked the IBC. So we have the International Building Code, and the governing bodies that reside under them are CISCA, ASTM, and ACE 7. And it's an engineering company. And so our engineering body. And so we've tracked data, and what happens is we don't just want to design for the quake itself. We want to design also for the secondary aftermath of the quake. So the earthquake can hit, but what happens is it causes more devastation if things in the building are not put together correctly or seismically braced or supported in the way it needs to be. So some of the secondary events or effects could be something moving in the building, causing a utility to come disengaged from where it's at, fall down to the ground, causing more destruction. Or we see where a building will shake and move, and the facade of the building, now the bricks start falling off and causing destruction and damage. So not only are we looking at the earthquake itself and the seismicity of it, but we're also looking at the secondary effects to see how we can best solve for those. And so over time, through the history and tracking the data, scientists and engineers have come together to put some variables together. Okay, how do we design against? What are the scenarios? What are the situations? What are the areas in which we need to focus on to defend against the seismic events. And so they came up with these three variables. The variables are geographical area, building types, and soil conditions. And sometimes soil conditions, people question that a lot. What does soil have to do with a seismic event? And so we'll get into that. All right, so these are used to determine what type of building can be built and where. So we look at geographical location, and we base that on, okay, how much seismicity is happening, or how much seismic event is happening in these different areas, because across the country, and we're going to get to a map here in a minute, and we'll see, across the country, there's different seismic forces that happen in different locations. When we think about California, high seismic zone. When we think about Hawaii, high seismic zone because it's also volcanic. And believe it or not, South Carolina is a high seismic zone. But when we talk about the middle of the country, it's a lot less. So geographical location really helps us understand how to build and how to design for. The building use, what type of building that we're going to be building for. We want to look at standard commercial buildings and go, okay, we need seismic forces to go inside of those, but what types of seismic forces? Are they the same that we should design for in hospitals or schools or other types of buildings? So we look at building use and decide what type of seismic application and how serious and how strong do we need to design against it. And then when we talk about soil types, there's many different soil types. Hard rock, very dense soil, stiff soil, special soils. We have soils where they've moved soil from one place to another to build up an area, and then they build upon that. And that becomes a liquidation factor or liquefaction when an earthquake happens and there's moisture involved. So soil types is very important in how we design. I told you there's a map, and here's our map. And so as we look across this map of our seismic forces, the highs and lows of seismic forces, we look at the previous map, and this was from the 20s and 30s, where they looked at seismic events, tracked them, and gave it values. And so we see the red values are the higher seismic zones. You can see California is in there, Utah, Idaho, even Washington and Oregon. And then we can look to the eastern side of the new IBC map and see that it's added on South Carolina and some of the areas in the central where St. Louis is at. So we use these geographical locations to understand how much seismic we need to build against, so we know where we're building and that we need to build stronger when we look at these areas. And we have some pictures here from 1971, and this goes to both building use and geographic location. So this building was built in Southern California. This is the Olive View Hospital, and it was actually built in 1920. So there wasn't a whole lot of seismic design and criteria around it. Even though they did recognize that seismic events happen, they designed the building as strong as they could or up to the knowledge that they had at the time. And so when the earthquake happened in 1971 in San Fernando, we can see the outcome of that. It was devastating. The building had no significant value once the event was over. Everything, the supporting structure was pretty much gone, and the building was a loss. So the seismic community got together and said, we need to design better. We need to look at seismic and look at the variables and also look at the building types and go and say, what's needed at the end of a seismic event? Well, hospitals, fire stations, police stations, things of that nature. And so we want to design a little better around these types of building uses. And when we look at the geographic location, this was California, which is high seismic area, they made some changes. And in the changes, we can look here on the left. The previous, it was a magnitude 6.6. And fortunate for us, as unfortunate as the circumstance was, they rebuilt the Olive View Hospital in 1994, or after 1971, and it had another event in 1994, which was a similar event, a similar area. So in this picture, we get to see what seismic design has done in those 20 years, how we look at the outcome of the 1971 quake and go, that was a devastating quake, and the outcome, we lost the building. And then in 1994, we can look at the seismic applications that we developed and said, those are good. We only lost a few windows. The building is still functional. These services are still functional. So we're on the right path. We're on the right track to getting the right solutions for our communities. So when we look at soil types, there's risk factors, right? When we talk about the soil types, rock. So San Francisco is built on a rock. New York is built on a rock. But San Francisco still has a lot more seismic events. And so even though it's built on a rock, we still have high seismicity, which is this high seismic movement and motions in San Francisco. So we can't build the same in San Francisco as we do in New York, because the seismic scale is different in its motion and its intensity. So we look here and go, okay, what are we looking to build? And so in this is the IBC, and this is where the importance of the IBC taking over and recognizing seismic is a very important factor. And so they take our three variables and put them in this. It just stated it a little differently. And so number one, risk category, right? That's our geographic area. Then we talk about the site class. And we talk about that's our soil type. And then we talk about number 6, the seismic design category. And that's the area in our geological where we have higher and lower seismicity to build for. And so the IBC took it upon themselves to state that everybody needs to design for seismic. So here's the statement that they put in here. The following information related to seismic loads shall be shown, regardless of whether seismic loads govern the design of the lateral force resisting system of the structure. So across the country, even if you're in category A and B, we still design for the seismic rating for that area, so we know exactly, or not exactly, but closely what that building will be able to withstand. All right, now we're going to look at discerning the differences in our geographic locations, because we have different seismic areas that have high and lower magnitude or forces that we want to build for and design for. So we have 3 different variables. We have 3 different geographic locations. And the categories are A and B, C, and D, E, and F. So as code passes down from the transition from the UBC to the IBC, what happened was the UBC handed it over to the ICC. So the ICC, the International Code Council, governs all the building that happens in the United States. It allows for other organizations or code bodies to participate and help them in its design as well as its inspection, making sure that everything is done right. So the ICC, under the ICC is the IBC, the International Building Codes. So the IBC is in direct relation. So all the data that we've gathered over the years from the seismic events, and when we talk about the variables and all the site conditions and everything, it all comes into the ICC. So then the ICC takes it, breaks it down, and they come together and they build the IBC. And so that's our International Building Code. This is the building code that we use to build and design our buildings around. And within the IBC, ASCE, which is the American Society of Civil Engineers, they help us know what it is that we are to engineer against and what numbers we're to use and how everything goes together as far as for that building in its loads. And it's not just seismic loads, it's wind loads, it's snow loads, it's rain loads, it's all kinds of different loads, but the seismic loads are built within the ASCE, and so it helps govern how buildings are built within the IBC. And then part of that, where it comes down to ceilings, we get involved with the ASTM. And so the ASTM actually is under the ASCE in the sense that the ASCE has transferred the responsibility to ceilings to the ASTM. So the question we get a lot is, where do we find the seismic information in the construction documents or in the set of plans? The IBC determined that we need to know that as installers and contractors, but we need to find out who is responsible for designing those, who is responsible for putting those numbers together, for telling us what category we're building in and what are the requirements within that. So the IBC put together a requirement for all the architects and engineers, and this is where the requirement comes across from the IBC, because we at the bottom end or at the end of the installation in ceilings, we're installing ceilings. The building, we're hoping the building is installed and built to the design specifications for the area that it's being built in for seismic loads, wind loads, snow loads, and all those things. So the IBC here tells us we need to have documents in order. And then they tell us that here's where we are to find them, the general structural notes. Now, we don't always find them here in the general notes. Sometimes we have to look around to find them, but it's nice when we do find them in the notes. And as we look through here in the general notes, here's what they have, the architect and the engineer has designed for. So we have risk category, roof snow load, floor live load, common use exterior deck and staff, stairs. And we get down to the bottom, and I want to highlight this. This is the earthquake load. So this tells us what seismic design category. So we were looking at the map earlier where we have reds and blues and greens. And so we look at this in the general notes and say, okay, the seismic design category that we're building is in category D. Down along the bottom of that, I'm just going to fill in a little bit of, these are seismicity ratings. So inside of that red zone inside of California, there's different numbers. The seismicity numbers change based on the intensity of the seismic area. So we might build a little different in San Francisco, even though the whole state of California is in category D. We build differently in San Francisco than we do in, say, the Central Valley, where there's not, the seismicity is lower. So we look along the bottom, it says S of S, 1.30. So that's the design seismicity that this building was designed for. We move that same building over into Utah, and that S of S might be 0.8 or 0.7 or 0.6. So that helps us understand what, well, it helps the engineers understand what they're designing for. And then the IBC transfers the requirements of ceilings down to the ASCE. So this transition comes across, and in the ASCE 13.5.6.2.2, we find that the responsibility for installation of ceilings does fall to the ASCE, but they are transferring that across to the ASTM. Acoustical tile or lay-in panels, ceilings in seismic design categories D, E, and F, as well as C. It's not stated here, but C is in there as well. Shall be designed and installed in accordance with ASTM 635, 636, and ASTM E580, Section 5. So when ASTM received that responsibility, they put in another 3 variables because they also saw, based on experience, that ceilings responded differently. They don't respond like every other part of the building because they have multiple parts that are tied together, multiple ends that are tied to different types of walls, soffits, and so on. And so they developed 3 requirements for ceilings so that we can install them for seismic. So one of them is independent safety wires for lights and utilities. Lights and utilities are heavier than our ceiling systems. So when there's an event and they're shaking around and moving, they can disturb, disrupt, or come disconnected. If they do, there's safety wires in place based by the ASTM requirements. Also, minimum strength requirements for the main T's and cross T connections. Now that's to the manufacturers. So we as manufacturers look to say, what is it that we are designing for? How are we designing and building and testing our grid to meet the seismic requirements? And so within the ASTM, we see that we have a minimum strength requirement for the connections of our cross T's and main T's. And then they also stated that spreader bars are required at the perimeters. Spreader bars keep the terminal ends tied together. They're right there within 8 to 10 inches, somewhere where the cross T's and the main T's tie into the wall and the wall angle. Because what happens is when a seismic event happens and it starts shaking, the walls move and impact the ceiling. And if the walls move and impact the ceiling and the ceiling starts to fail, then it could cause a cascade effect where not just one portion of the ceiling fails, but the entirety of the ceiling can fail. And what ASTM recognized through experience, it wasn't through engineering, they saw what happened at the North Ridge and the Loma Prieta earthquake, that the perimeters come apart. And when the perimeter T's come apart, the tiles start falling out, which causes this cascading effect. And then the ceilings start coming apart. So these are the 3 requirements that are actually baked into the ASTM E580. So now we're going to get into what the installation requirements are and how we are using all the data and how it is transitioned all the way from the data that we have discovered over time and put together into engineering for seismic requirements. It traversed into our seismic documents and into our architectural plans. And now it's going to come out as installation requirements through, for us, the ASTM E580. And with that, I'm going to hand this over to Stephen Bell, our product manager for ceilings.
All right, thanks, Michael. Appreciate that. Hopefully everybody can hear me okay. So in this next section, we're going to disseminate the ceiling installation requirements. So basically dive into what that means for our installations of ceilings. And so this plays right into my background and experience of designing for seismic installations. And so what I'm going to do is explain what the requirements are for each seismic category. There are 6 seismic categories, A through F, and they're broken up into 3 tiers, A and B as the first tier, C is the next tier, which will be moderate seismic activity, and then the last tier is D through F, which is has the greatest seismic activity. So for categories A and B, there's minimum installation requirements. As you can see from the top, there's one item, it says, let's install for ASTM E580. So we need to make sure that the ceiling is square, we need to make sure the ceiling is level. As we move on to category C, we're not only designing for ASTM E636, but also E580. And so I'll read through this, highlighting a couple of the key points, and then the subsequent slides, we'll start seeing some of the ceiling details. So for category C, intermediate duty is acceptable. If your ceiling is over a certain weight, you will need to bump up to heavy duty grid, but for the most part, intermediate duty grid is fine. And then it states that you need to use 7/8 inch minimum wall molds or greater, and there are no hanger wires required at the perimeter. If you reduce the size of the wall mold to something like 9/16, then you will be required to install perimeter hanger wires within 8 inches of the wall. All 4 sides must have a gap of 3/8 of an inch between the end of the T and the wall, and this will allow the ceiling to move in a seismic event. Next, you need to keep the T ends together, or tie the T ends together with a spreader bar or stabilizer bar. And then there is an alternate installation using a perimeter attachment clip, or what USG calls ACM7, which will allow the installer to replace stabilizer bars with this clip. And so USG has been approved per ICC to allow for an alternate installation in category C, where two sides will be fixed or attached to the wall, and then two sides will be floating or loose with a 3/8 inch gap. So we can start to see how that breaks down in the next two slides. If you can go to the next slide, Michael. Right, so here's a perimeter category C detail based on ASTM E580. The stabilizer bar is visible in the center of your screen. A 3/8 inch gap typically is required, typical around the entire ceiling, and then 7/8 wall mold. And so on this next slide, you can see the alternate ICC approved method that uses the perimeter attachment clip, or ACM7. So the perimeter attachment clip will replace stabilizer bars. And then there is what is called a fixed side and a floating side. The fixed side keys are installed tight to the wall. Through the clip, there is a hole, or there are two holes at the top of the clip that will be fastened tight with a screw. And so that will be your fixed side. And then on the right-hand side of your screen is your floating side. Now you'll have a 3/8 inch gap between the wall and the end of the T. And then the screw is actually installed in that center slot, and it's installed loose to allow for the ceiling to move in case there is a seismic event. And so now we're going to move on to categories D, E, and F. And so again, we're installing for ASTM C636 and E580. And as you can see from the screen, because we have increased seismic activity in these areas, there are a lot more requirements. So we're taking up a full slide here of everything that you need to account for. So first thing I'll highlight is that for categories D, E, and F, heavy duty grid is now required. You can no longer use intermediate duty grid. And there is a 2-inch minimum wall angle that must be installed around the perimeter of the ceiling with the use of stabilizer bars. There is not an alternative method, but there is a separate installation method that uses that allows for the use of 7/8 inch wall mold when you use the perimeter attachment clip, such as an ACM7. And then two adjacent sides need to be fixed, like I kind of mentioned before. And then two adjacent sides need to be floating, but now the gap is a lot bigger. The gap needs to be 3/4 of an inch to allow for more movement to occur instead of 3/8 of an inch for category C. Keys need to be tied together with stabilizer bars or spreader bars, unless you use the ACM7 or perimeter attachment clip. And now perimeter wires or hanger wires are necessary on every key all the way around the ceiling within 8 inches of the wall. The next couple things I'll highlight here is lateral force bracing. So lateral force bracing needs to be installed for ceilings that are over 1,000 square feet. And the lateral force bracing is installed every 12 feet on center in both directions. And then for ceilings that are over 2,500 square feet, expansion joints are required for those ceilings. And so now this is a perimeter detail for categories D, E, and F. And as you can see from the screen here in the center, we're showing the stabilizer bar. On the lower left-hand side is that large 2-inch wall molding. A 3/8 inch perimeter gap is shown, and then perimeter wire within 8 inches of the wall. And so I'll just highlight here, designers and building owners tend to not like such a wide molding along the outside of the wall. And so the secondary method or separate method using the perimeter attachment clip is approved for the code, which we'll show here now using, again, using the ASTM 7 clip. So when you use the perimeter attachment clip, you can swap out the 2-inch molding with a narrower 7/8 inch molding. You still need a fixed side, like I highlighted before. Hanger wires need to be installed with 8 inches of the wall. And then on the floating side, you can see that the screw is installed within that slot to allow for movement, and the gap of 3/4 of an inch is shown, is required on 2 floating sides. And so for ceilings that are over 1,000 square feet in size, lateral force bracing is required for the code. And so that detail is shown on the screen now. And there's a lot going on. And so we've tried to highlight the key components of lateral force bracing. So first, highlighted in green is the vertical wire. So the vertical wire is part of our standard installation assembly. And it is, the purpose is to counteract the gravity load or downward pressures that are installed on the ceiling. Next up are the splay wires, which are highlighted in blue and red. There's 4 splay wires installed on a 45-degree angle, and it needs to be attached within 2 inches or less of the main T cross T intersection. So two of the wires, let's say the blue wires, those are your north-south wires. They are aligned with the main T, and then the 2 red wires, the east-west wires, need to be aligned with the cross T's. And then lastly is the strut. So this is typically a metal stud that has some structural integrity to resist upward forces imposed by the splay wires and the upward forces imposed during a seismic event. So as the building moves, it pulls the splay wires up, which in turn pull up on the ceiling. And so the strut keeps the ceiling from jumping or moving upward. And here's a layout, a ceiling layout of when you need or where you need to provide lateral force bracing. So you start 6 feet from the wall, and then you move outward on a 12-foot by 12-foot on-center grid. And you can see on the screen those locations are highlighted in red. And so when you have ceilings that are over 2,500 square foot in size, seismic separation joints are required. The seismic separation joints break up the ceiling into mostly equal sizes, and you break up the ceiling in mostly equal sizes, and that allows for movement to occur in these larger ceiling areas. And so there are special clips that need to be installed after the ceiling is installed. You can install these clips that will allow for that movement to occur within the ceiling. And so next, I'm going to turn things back over to Michael, and he's going to walk you through some of the key exemptions that are stipulated within the code. So go ahead, Michael, take it away.
All right, thank you, Stephen. So the exciting part for me in the codes is, as a seismic manager, is the exemptions, right? We like to have and see what the exemptions are, because within seismic, we never really get to use them very often, but when we have them, it's nice to be able to put them out there. So we have ceilings that are less than 144 square feet. So if I have a room that's 12 by 12 and it's 12 by 12, it's not 12 foot 1 inch, 12 foot 1 inch, it's 12 by 12. So ceilings less than or equal to 144 square feet are exempt from seismic practices. I have no idea what's going on. Sorry for technical difficulties. Where we have these smaller rooms, the code allows for no seismic application. You'll install it as per a standard category A, B. I apologize. The second exemption is ceiling areas of 1,000 square feet. So Stephen went over the lateral force bracing requirement. Well, the lateral force bracing requirement, where you have the compression posts and force splay wires, does not start until 1001, when your ceiling system is greater than 1,000 square feet. So the exemption is anything less than 1,000 square feet, we don't have to put in the compression posts and splay wires. And that is a lot of manpower and labor, especially when you get into building designs where there is a lot of information of technology up in the ceilings or in the plenum areas where it becomes difficult to install the lateral force bracing. So this exemption is really nice. And so if an architect wants to design a room without having lateral force bracing, they can put a seismically braced soffit in there to bring the ceiling size down to less than 1,000 square feet and pretty much take away any need for lateral force bracing. Another exemption is in the gypsum, where you have a suspended gypsum ceiling that extends from wall to wall on single level. This has limiting factors into it. It's a gypsum ceiling. It becomes a monolithic membrane when it's attached to all four walls on a single level. And so it doesn't have a lot of movement. It really holds together well. Part of what we've done with USG is we're required to test our systems on what's called a shake table. And we've taken our gypsum suspension ceilings and built them and designed them and tested them as high as they could go and had no failures in our suspended ceiling. So I can see why this exemption makes sense. It doesn't depict what size ceiling. And that's something that seismic scientists and engineers are looking into right now. We can't just build an unlimited ceiling with gypboard, or can we? So we're looking at that right now. But right now in the code, it's exempt. If the ceiling goes wall to wall on a single level, then it's exempt from code. One of the more complicated exemptions is in our free-floating clouds. Free-floating cloud assemblies, because they're not tied into any walls, and typically there's utilities or lighting or different architectural components designed or built around these. The code allows for exemption because the way floating clouds operate, it's like a plumb bob. If you attach a plumb bob to something and you move that something, and the plumb bob is only extended down, say, a foot, the plumb bob itself moves quite a bit. But if you take that same plumb bob and drop it down 3 to 4 feet, and that something that is tied to moves, the plumb bob does not react the same way. It's very slow in its reaction time. So ASTM recognizes that and allows for free-floating clouds to be exempt from seismic requirements, but it has also stipulations. In 8.1, it says the design load for such items shall equal 1.4 times the vertical operating weight. Whatever that ceiling system weighs, the support should be able to overcompensate that by 1.4 times. Seismic in 8.2, seismic interaction effects shall be considered in accordance with 5.7, which 5.7 in the ASTM talks about it cannot impact a utility that could cause failure to the building. If there was an electrical component, or say a fire sprinkler, where there was a seismic event and the floating ceiling moved, impacted that, and caused a failure, then that is not allowed. So when the designing of the floating clouds are happening, architects and designers need to look at what is around so that there's no failure could come from the seismic event. And the other one, the last one, is the connection to the structure shall allow for a 360-degree range of motion in the horizontal plane. Now, the horizontal plane is actually a radial plane. For the most part, when the building moves, if it's a cloud, it's going to move on a horizontal plane, that it's going to move in a radius action. So when we're designing for that, and we want it to be exempt, we can't have anything in the peripheral of the floating cloud where it's going to impact. It's part of 8.2 similarity, but it's a little more clear in the sense that 8.3 says we don't want to have anything in its motion path that it could impact or damage or destroy or cause failure. So those are the exemptions within the ASTM, and they're right in the beginning of the ASTM. The main thing is to have the right documentation, supporting documentation, and understanding what we're designing for in the building. And each one of these, well, two of the three have complications in them in the sense that we have the ceilings less than 1,000 square feet. Anything more requires it. The gypsum ceilings, we can't have elevational changes, and it must attach to walls to be exempt. And then the free-floating ceilings have quite the criteria within themselves. And a lot of architects like to install or insert these types of architectural designs in because they look really nice in the buildings. But when we're designing for category D, there are a lot of stipulations that we need to look at. And so we're continually looking at how to design the ceiling, the free-floating ceiling, to meet the seismic criteria. And with that, that ends our presentation for the day, but we're going to move into question and answers. And with that, I'm going to hand this over to Tao for our question and answer portion of this.
All right, thank you, Michael. A couple questions came in here. What happens in category D when a ceiling changes elevation?
So when a ceiling changes elevations in category D, what happens is that transition in elevation is like it's a wall. It becomes a perimeter detail. So part of that ceiling, that transition needs to be rigidly braced like it would either the fixed or the floating. So at that elevational change, you need to determine which end of the ceiling, say on the lower plane, is attached at the wall, and what is that attachment? Is it fixed or floating? Let's say it's floating. Comes out, and that transition, so at the other end of that ceiling where it transitions up, that needs to become fixed. So we would have to put rigid bracing in that so that we have a fixed and a floating side of the ceiling. And just for clarification, the 3/4 inch gap and the 3/8 inch gap that is required by the ASTM, that is for the movement of the wall, not so much the movement of the ceiling. The movement of the wall, they found that the walls bow and move during a seismic event, and they can compress. And so if they compress against the ceiling, it could cause failure. So that's where the gaps at the perimeters or on two sides of the perimeters come from.
So also from category D, do we always have to use perimeter wires?
Perimeter wires are required for ASTM on every cross-tier main tee. But in some situations, and it's kind of funny that it came from OSHPD, or the Hospital Designers is now HCAI, where they're building and designing hospitals. In hospitals, they allow, if the perimeter tile or the perimeter cross tee is less than 8 inches, then we do not have to put a perimeter wire on that ceiling. So we're trying to figure out how to parlay that across into the rest of the industry. So it says, based on ASTM, yes, all perimeter wires are required, unless somebody else says they're not.
So it says in clean room application and category D with the alternative system, if we use the US 29 CE, it is an exemption for use the ACM 7 clip.
Clean room application has a little different design, but yes, as long as there is the ability to have the 3/4 inch on two opposing walls, then yeah, it doesn't go into a channel at the perimeter. So I would have to see the detail in that to really clarify the question, because it's a little bit vague. But in a clean room environment, you're still going to use the ACM 7 clip in the floating,
and then
or in the concealed.
Okay. So this is a long one, so I sent it in the chat. I'm not sure if you're able to read it, but it says from the title, ASTM E580, standard practice for installation of ceiling suspension system for acoustical tile and lay-in panels in areas subject to earthquake ground motions. Is this a guideline for installation? Does it use C636, C635 as a base? And how does it apply to C1925?
Okay. I would have to read through that again. Basically, ASTM dictates that C636, C635, they only apply in specific categories, right? So if we're designing in category A and B, then we're going to use 635, 636. If we use category C, we're going to use 636 and ASTM E580. And then category D, ASTM E580. So when we're talking about in conjunction with other ASTM requirements, we would have to look at the condition and the actual structure and the design of the building to see if there's anything alternate other than ASTM E580 that needs to apply to that. And I don't know that I answered that question, but I would love to take that offline at some point to get clarification for our person that's asking.
I'll write that down and send that to you. And here's a shorter one. As the 1,000 square foot rule changed recently in the San Francisco Bay Area?
No. As the 1,000 square foot rule has always applied, the challenge that came out when it first happened in 2006 was they didn't understand the 1,000 square foot. So everybody made it to where lateral force bracing was required in every instance. What happens is the building inspector doesn't know the code completely, so they make them put it in sometimes. And part of my job is to go through and educate the code officials on seismic, because they have to know seismic requirements for every product. So I try to help them understand for ceilings, for our contractors, what those seismic requirements are. So there has been no change in the ASTM for the 1,000 square foot rule.
Okay. So the next question is, what are the strength, load, capacity requirements for the vertical struts?
Okay. Those are based on plenum depth. So if you've got a plenum that's, and I've seen them this last week, 35 feet, how do we design for that? So each one of those areas of depth, and we at USG, I actually have an engineering report that shows from 2 foot all the way up to 17 feet, I believe, what those gauge materials are and the shapes and sizes of the metal studs that are used. So they vary based on plenum depth and seismic criteria. So they're not all the same, but basically you can use anywhere from a 25 gauge to a 18 gauge strut for resistance, for upload resistance.
What is the process when using, I'm not sure I'm saying this correct, TEG or TEG edge tiles, as scribing will surely lock the ceiling up?
Okay, so when we talk about tile, and I've had this discussion with OSHPD and many other inspection organizations, the tile doesn't matter. Even though we see that the tile does have some confinement or binding effects on it, the tile, when it comes to earthquake motion, is a material that is compressive and it'll break apart, and it won't impact the outcome of the ceiling per se. So we don't worry about regular edge tile. We can cut it in or not cut it in. It can be tightly fit if it's a full module on the perimeters. It doesn't impact the seismic requirements. So we build the grid with the, according to the ASTM E580, and then insert the tile accordingly to make sure that it looks good in the end result. So the tile, we don't have to worry about tile, but when we get into metals and woods, then we have some different scenarios that we look at when it comes to DSA regulations and OSHPD regulations, or schools and hospitals governances.
And last question here. Having a 3/4 inch space at a 7/8 inch wall mold is quite unforgiving. Have you ever encountered a problem with this type of installation?
The installers have come to cut those NTs really clean, and so the 7/8 or the 3/4 inch gap only allows for an 1/8 inch. USG has we pretty much developed a perimeter wall angle that's a little wider, so it's 1 1/8 wide. But again, everybody has come. They're so used to cutting that grid and leaving that 1/8 inch that it's not typically any problem to any of the installers. And then the use of the ACM7 clip, that's what helps sustain or keep that cross T level during a seismic event, keep it up above. And also, that's also why there's a perimeter wire required in category D. So it can be complicated, but for the most part, everybody is pretty used to cutting the cross T's that tight. We don't typically see many problems with that.
Well, I think that concludes our Q&A session. So on behalf of AWCI, thank you, Michael and Steve, for the informative presentation about seismic ceiling design. And attendees, thank you for joining us today. We hope to see you next time. Have a good rest of your day, everyone. Bye now.
Thank you. Bye-bye.